Hello class, welcome to the second part of 3.3, polar coordinates. We will start off with this part, transforming polar equations to rectangular coordinates. Okay. So first question is theta equals pi over 3. So this is an equation, as you can see. It's not represented as a coordinate, it's given as an equation. And we have to transform this polar equation to rectangular coordinates, to an equation in rectangular coordinates. Okay, so technically, I would say xy equation, an equation that contains just x and y. This equation contains theta, but it, generally it'll have the r and the theta. In this case, they just gave us the theta. Okay. How do we approach this? Now, remember, you want to rewrite this equation in x and y. So your focus is always trying to get into x and y. Now, we don't have the r, so we have only the theta. Use the relation that involves theta, x, and y. The relation that involves theta, x, and y is tan theta equals y over x. So keeping that idea in mind, we apply tangent on both sides. What this does is it, let me just show you in colors. We're applying tan on both sides. So tan theta on the left, remember our focus was to use tan theta, so that we applied tan. Tan pi over 3 gives you a specific answer, which is √3. Right? We also know that tan theta itself is y over x. So you got y over x equals √3, just like that. You were able to convert this into an equation just involving x and y. So go ahead and solve for y equals √3x. In fact, what you get here is the equation in the linear form. So I'll just say linear equation. Okay. Next, B. This is interesting. This equation just has the r. Previously, we had just the theta. This has the r. So go ahead and see if you can use the relation that involves x, y, and r. So we have seen that x squared plus y squared equals r squared is a relation. So we have to square both sides because that relation has r squared. Let's show the squaring action. That is r squared equals 9. Therefore, you can go into the x squared plus y squared equals r squared formula and simply insert 9 for r squared. And that equation actually resembles the template of a circle, right? Equation of a circle. So this is the equation. So being familiar with these templates and how they look is very essential to knowing what the shape will be. Equation of a circle. There is no center, there is no h comma k there, so the center is 0, 0. And radius has been squared, so the radius actually is 3. 3 was squared, right? So got that. Pretty easy, it's just a manipulation of using relevant relations. Let's see an equation that involves both r and theta. 6 cosine theta minus 8 sine theta. Okay, once again, we're going to multiply both sides by r. And that will be r squared equals 6. I want to put the r there, cosine theta minus 8r sine theta. We like this trick because this R cosine theta is defined to be x, and R sine theta is defined to be y. So we got the x, y, and the R very close. R squared equals 6x minus 8y. Okay. Now, if we get rid of the R, we got everything in x and y. That's kind of easy because you know R squared is nothing but x squared plus y squared. So look at that. R becomes x squared plus y squared, and the right-hand side remains as it is. So we have reached the point where everything is in terms of x and y. Fantastic. But then we have to go back and clean it up because this form does not reveal to us the shape of the graph. So we want to make sure that this is written properly so that we understand the shape more clearly. Okay. We've seen this technique before where when we had a splatter of x and y, x squared and y squared, then we have to use completion of squares. So we use completion of squares. Squares. What happened there? So for that technique, you want to first bring them all on one side. Make the other side equal to 0. Okay. And then collect all your x's and your y's together. X squared minus 6x. If you had one more term, right? If you had one more term, that will complete the square there. Then you look at your y. There's y squared plus 8y plus one more term there would complete the square for the y's. This is 0. So whatever you add here, make sure that you have its corresponding term added that side as well. Okay. All right. Remember the technique? We said you have to do the negative b over 2. So this is negative b in the quadratic form. Okay. Remember, this is quadratic completion of squares. So negative 6 over 2, the whole squared. That's what happens here. That reduces to a negative 3 whole squared, which is 9. And for this one, I apologize. It was not a negative b over 2. It was a b over 2. B itself was a negative here. That's what I was supposed to say. All right. So this is b over 2 here as well. So b over 2, the whole squared. That comes out as 4 squared, which is 16. Right? Therefore, you come back here, 16 on the other side, and 9 to be added on the other side. Remember, we are grouping these 3 and these 3. Okay, so you get two perfect square binomials. So x squared minus 3. Remember, we mentioned about how this comes into, not x squared, x minus 3, because it's a minus 3 there. That becomes the first binomial plus y. That's a positive 4. That's plus 4, the whole square. And on this side, add the 9 and the 16, you get 25. So now I'll kind of clean it up, bring them closer. X minus 3, the whole squared, plus y plus 4, the whole squared, equals 25. Okay. I always like to go back and quickly check the signs. Got that? And what do you think this is? Interestingly, this is also the equation of a circle. But this time we have specific center and radius. Equation of a circle with center 3, negative 4 and radius 5, right? Because your radius was 5 units, right? 5 squared, 55. Now, I'd like you to go through the book, to the ebook, to check for other shapes that you will see coming out of different equations. I want you to be familiar with those shapes. I'll try to present a few here, okay? Let's remember a couple of things. The polar axis, when we say polar axis, we mean the x-axis. When we use the word pole, we mean the origin. So I'm going to call upon that later, but let's remember this. Polar axis implies x-axis, and pole implies the origin, 0, 0. Okay? So now we have, if we had a line passing through the pole, okay, I want to create actually, what do I say, 2 columns, or maybe 3 columns. Do that here. That way I can space it out. Okay. Line passing through the pole is the origin, with a slope tan k. Where k is a theta. Okay. So then theta equals k. So if this was how you have your angle, k is some value, right? Then your graph, I'm going to just sketch it, 1, 2, and 3. Okay. Then your line would actually be a line that passes through the origin. And that's a line passing through the pole with a slope tan k. So this is exactly your y equals x setup, right? It looks like that, but it's not necessarily like that. It looks like that. But it can be like theta equals pi over 3, right? That will look differently. This looks more like pi over 4, theta equals pi over 4. But you have your line passing through like that. Okay. Next, if it was a spiral, a circle, that first one was a line, right? So if you want to know if the formula, the equation will produce a circle, then you have r equals a cosine theta plus b sine theta. If it looks in this form, you can be assured that it's going to be a circle. These are like templates again, for us to know how these will behave. Once again, in fact, we did an example of a circle. It went like this. Remember? So that's how it might be sitting. Okay. Maybe I should use a different color. Purple kind of coincides with the blue. Okay. How does it appear if I had a spiral? Spiral, think of the snail, kind of setup. So that's going to be r equals a plus b theta. There are these, naturally occurring shapes also, like the snail, also have a symmetry about it. So it's really important that we see that. It can happen. You have to go on like that. And this could be a case where r is theta over 3. Okay. Then how does a cardioid look? Cardioid. Remember fun with cycloid and hypercloid? We have cardioid. This is a times 1 plus cosine theta. Could look like that. 1 minus cosine theta, 1 plus sine theta, or a times 1 minus sine theta. Any of these forms would look like this. Cardioid. Of course, it's something so close to cardio. In fact, the word cardio is there. Right? So think of it as cardio, which is heart-shaped. Okay, so that's how it's going to look. It's going to be the heart-shaped figure, but the heart is sideways. So I'm not drawing all the circles. Okay, you should understand that this is a polar grid. Just to avoid too many things, I'm just trying to draw the shape. So I hope you can understand that. Okay. It could look like this, or it could look more like a bean. It just depends on how we are trying to shape this. Okay, so anyway, cardioid would look like this. This is, in particular, cardioid that would be like this: 3 times 1 plus cosine theta. That means the third circle, it's going to touch the third circle in some order. Remember that? Well, the book does a nice job, of course, of drawing the shapes and giving you the exact equations for those particular shapes. Then we have something called limaçon. Okay. That will be R equals A cosine theta plus B, and R equals A sine theta plus B. It's interesting that you see these kind of shapes in nature, right? And you can give mathematical modeling to these shapes. And you can think of them as flower petals or some sea animals, you know. They have these beautiful patterns. I'm sure you must have watched all these documentaries. It's unbelievable, their colors and their shapes and their symmetry and how sometimes they build their nests. Also, you know, it's all so mathematical. The patterns are unmistakably, you know, symmetric. So, so we are naturally interested in that. And now when we discover more and more about deep sea animals, it's unbelievable how you know, math runs so close to nature, right? Okay, so it's like you had this circle and then another one, right? We've seen these in flower patterns. So this is really cool. So this is how an R equals 2 plus 4 sine theta will look. We've done the graphing, right? So if you're really curious, you can graph these. You will see that this produces these patterns. And of course, the famous rose pattern. And for a rose, the petals, you want A cosine B theta, or AR equals A sine B theta. And for this, you will have beautiful petals. Which I can draw them beautifully. Somewhat better. R equals 3 sine 2 theta. Okay. So these are some of the shapes that we can see, and there are many, many, many more. But this is just enough for us for this level. So I just want to point out to the rows, okay, there are more things. So symmetry really comes in, and that's the next subsection we're going to learn, next objective. So a quick look at that. Okay, in rows, the petals are very clearly indicated. Defined, right? Okay. Well, let me draw the petals for you. So if you had, you know, compare this with what we have there. There it was within each quadrant. Here it is kind of overlapping in 2 quadrants at a time, right? And look at this one. This one has 1, 2, and 3. It's like a fan. Okay? This is R equals 3 cosine 2 theta. And this is R equals 3 sine 3 theta. So we're going to compare these things and see how, is there any pattern we can detect. So if coefficient of theta, right? Coefficient of theta is this part, right? 2 theta or 3 theta. So the coefficient of theta is even. It implies twice as many petals. I mean, I'm showing you only 2 of them, but if you were to explore more and more shapes related to this equation format, then you'll begin to see this unfold. So if and you can test it using Desmos as well. So 2 theta would give you twice as many, so 4 petals, 2 times 2, 4. If you had 4 theta, because it has to be even, right? So if you had 4 theta, you'll have 8 petals. And if you had 16 theta, you'll have 32 petals and so on. Right? So likewise, if coefficient of theta is odd, it implies it is equal to the coefficient. Look at this one, 3 theta, it's odd, right? Coefficient is odd. Therefore, the number of petals will match with the coefficient. So you have 3 theta, 3 is the coefficient, and there are 3 petals. Okay? And then if the coefficient of theta is not an integer, then there are 2 possibilities. So then we have irrational, right? If it's irrational, √3, √2, e pi, something like that. Irrational coefficient implies the curve does not close. And if it is rational, the coefficient, it implies the curve is closed. So what's the example? Let's say example would be that if say R is 3 sine 5 theta over 4. Look at the coefficient. Coefficient is 5 over 4, which is rational. You can, without even graphing or looking at the picture, say confidently that the curve is closed. On the other hand, if R equals, say, 3 sine pi theta, because pi is irrational, the curve never closes. Next, we talk about symmetry in polar coordinates. Okay, so I have some conditions that will help us to determine what kind of symmetry there will be. And so I'm just going to list them out. Okay. Symmetric about the polar axis. And, if you can recall, the polar axis is the same as your x-axis. Then r comma theta will be the same as r comma negative theta, or r comma theta will be the same as r comma pi minus theta, using reference angles. Okay, 2. Symmetric about the pole. Pole is the origin. Remember symmetry about the origin? We used to call it I mean, in XY situation, we would call it symmetry about the origin as odd functions. Here it is symmetric about the pole. Okay. So here's it. If r comma theta and r comma phi plus theta are on the graph, it implies r comma theta is negative r comma theta, or r comma theta is r comma theta plus pi. When we do the problems, you begin to understand this differently. Symmetric about the vertical line, theta equals pi over 2. Again, a quick parallel in the xy coordinate system would be your y-axis, right? That's your vertical line. Here also pi over 2 is your vertical line coinciding with the y-axis. So you got that. Think of this as a y-axis. If r comma theta and r comma pi minus theta are on the graph, it implies r comma theta equals negative r negative theta pi minus theta. Okay. So how does it look? Well, symmetric with respect to, WRT is with respect to polar axis would be, and say we had and you had r comma theta, right? You can see the symmetry polar axis would be, and this was the equation of 2 minus 2 cosine. And symmetry, the polar axis is your x-axis, so it is just like a reflection. You see a corresponding point on the other side. With respect to the pole, it might look like this, like an 8. And remember, it's across the origin, so it's the pole, right? So that's going to be negative r comma theta. And they gave us the equation for this one to be 9 cosine 3 theta minus 2. I mean, you want that beautiful 8-looking graph. The equation will get a little complex. Symmetry with respect to theta equals pi over 2. This looks like this. I don't know, it somehow reminds me of a tomato. All right, r equals, I'll just mark the points, symmetric points. So this is about pi over 2, so it's the vertical axis, right? So think of it as left-right reflection. R comma theta here, r comma pi minus theta. This equation is r equals 2 minus 2 sine theta. Quickly, 2 minus 2 cosine theta was sideways, right? Cardioid, and r equals 2 minus 2 sine theta is sitting like, horizontal. It's a horizontal looking cardioid. All right, let's do a problem. Find the symmetry of the rows defined by the equation r equals 3 sine 2 theta and create a graph. Let's do the calculation part and then finally graph it, because that's the order also. Okay. Suppose r comma theta, we don't know, right? We want to find the symmetry. So we're going to suppose that r comma theta is a point on this graph, r equals 3 sine 2 theta, right? So we'll check each symmetry, okay? So symmetry with respect to polar axis. This symmetry says it's a function of theta, right? If r equals 3 sine 2 theta, it's polar axis, so f of negative theta r equals 3 sine 2 times negative theta. Because it's an odd function, the negative would come out, it would spit out the negative, okay? So remember to write that. And let's say sine is an odd function. And then you say, okay, if it was symmetric about with respect to the polar axis, then f of theta would, these two are not the same. Remember, coming back here, the theta and the negative theta, right? You should be able to find another point on the other side correspondingly. And that's not showing. I mean, it's not showing. I'm not saying it's not showing. I'm saying that these two are not equal for the moment. Okay. So if this is not the case, if you go back, right? Go back here, looking at the first condition. So you should have either this first condition to work or the second condition to work, isn't it? So the first condition did not work. That's what I meant. And so we're going to test the second condition. Does this condition work? Okay. And we'll come back and let's see, check that. Okay. Okay. So we have the second condition, and let's see what it says. Okay. Oops, I think I pressed something. Okay. I cannot see if this is recording. It says it is. So let's see. Okay, because I cannot minimize this. Oops. Okay. Let me assume it is recording. Oh. Okay. Where was I? Oh, let's go to the second condition. Okay. R comma theta negative r comma pi minus theta. Okay. R theta is equal to why this keeps showing up. Negative r comma pi minus theta. Okay. So f of pi minus, we already know what r comma theta, I mean with the theta was, so we just check with the negative r and the pi minus theta. So replace the r with a negative r and replace your theta with a pi minus theta. So negative r equals 3 sine 2 pi minus 2 theta. All right, now if you use reference angles, 2 pi minus 2 theta would actually come back as 3 sine negative 2 theta, okay? So reference angles. And then use the oddness of sine to pull out the minus, negative 3 sine 2 theta. Divide both sides with a negative sign, which implies you get r equals 3 sine 2 theta, which is the original equation. Okay, so this implies the graph is symmetric with respect to the polar axis. Next, we go to the second condition, symmetry with respect to the pole. We're collecting details to help us graph this, and you could go ahead and draw the table and graph it. Symmetry usually helps you to do it quickly, okay? Especially when those points were repeating, meaning pointing us or circling back to the same location, then symmetry really would come in handy. Okay? Instead of going back, I will just recall those conditions here. That was fine. So if it is negative r comma theta, let's test that by replacing the r with a negative r and the theta keeping it as it is. Okay. This is not equal to the original equation. So the first condition doesn't apply. First condition under this symmetry. So let's go for the next one, r and theta plus pi. So keep your r as it is, but 3 sine 2 times theta plus pi. Remember, you're replacing only the theta, so remember to keep the 2. All right, so this will be r equals 3 sine 2 theta plus 2 pi. The angle is this. How do we handle this? Again, go back to your trig identities. So sum identity, trig, right? And expand this. Because you want them, you have the 2 pi, so it's going to simplify, you know that. You only can retain the ones with the theta. Oops, this would be 3 times sine. Right here. This is what you're going to do, sine alpha plus beta, right? Which was sine alpha cosine beta plus sine beta cosine alpha. Recall that one, okay? All right, so this will be sine 2 pi cosine 2 theta plus sine 2 theta cosine 2 pi. Because it's being added, the order doesn't matter. But when we do have alpha minus beta, the order matters, so we need to watch out for that. So that's going to be 3 times sine 2 pi is 0. Sine 2 theta. Cosine 2 pi will be a 1. So this simply reduces to r equals 3 sine 2 theta. This is the original equation. You must satisfy one or the other, and you got one of them working. So this implies graph is symmetric with respect to the pole. Got that? 2 down. 3. Check the symmetry with respect to theta equals pi over 2. And for this, we had r comma theta to be either matching with this, or matching with, let's start out with negative r, negative theta. Replace your r with a negative r and theta with a negative theta. 2 times negative theta. Because of the minus, it becomes minus 2 theta. Then the oddness of sign brings the theta, the minus out. So r equals 3 sine 2 theta. Okay, it works right here. I mean, it works here, so you can actually stop right here. Equal to the original equation. Let's just quickly also do the other one. Okay, so see if it was symmetry. Keep the r as it is. Pi minus theta. Sine 2 pi minus 2 theta. So reference angles tell us that r equals 3 sine negative 2 theta. R equals negative 3 sine 2 theta. Once again, the oddness brings the negative out, which is not equal to our original equation. Because the first condition, one of the conditions was satisfied, it implies that the graph is symmetric with respect to theta equals pi over 2. All right, now we're going to pull all these details together. Remember where we started, okay? Because it's been a long time since we saw the question. And it's find the symmetry of the rows defined. So we're doing all this to find that rows or graph that rows. The graph using symmetry. Okay. And I'm going to draw 2 columns for theta and 1 for r. In fact, I'll make it 3 columns because collect the r comma theta. Theta. R is 3 sine theta, 2 theta. We go back to the original problem. This was it, right? And then we have r comma theta. Okay, 0. Previously, we saw that the pi over 4, pi over 2, the quadrantal angles kind of gave us, kind of bounced us back to the coinciding points. And so this time we're going to be extra careful and use other angles. Okay. So pi 0, pi over 6, pi over 4, pi over 3, pi over 2. Okay. So each time we want to get something that will help us plot a new point. And so that's going to be 3 sine 2 times 0, 3 sine 2 times pi over 6. Strategically use angles. Sometimes it won't give you the desired whole number. It can give you a decimal answer. That doesn't matter. Like in this case, pi over 3 is what you get, right? So pi over 3 will be root 3 over 2. And because you know it's going to be an irrational number, get the decimal value for this, 2.6. 2 times pi over 4, this will be pi over 2. 3 sine 2 times pi over 3. 2 pi over 3, so that again will be a root 3 over 2. Approximately 2.6. 3 sine 2 times pi over 2. You go away, get back the sine pi, which is 0, which is 0 here. So let's collect these coordinates, 0, 0, origin, 2.6, comma pi over 6, 3, comma pi over 4, 2.6, comma pi over 3, and 0, comma pi over 2. Okay. What we're doing here is, if you see the coordinates that we chose, and the angles that we chose, they went from 0 to pi over 2, just the first quadrant, right? So what we're trying to do is we are trying to graph the first petal. If you look at some of the hints we've seen before, so if the coefficient is even, it implies you have to have double the petals, right? So you are trying to see how the petal will distribute in the first quadrant, and based on how it will be, is it lying exclusively within the quadrant, or is it overlapping on the axis between two quadrants? Once you see that pattern, you can start filling in, because you now know we're going to have 4 petals. So that's the strategy here. So this is quadrant 1, okay? So these are just angles from quadrant 1, and once we plot that, we should be able to check the symmetry for the others. Now to this end, I have a grid here, okay? So this should be easy for us to begin to plot. All right, 0, 0. Got that. This is the actual polar coordinate, right? This is the polar axis here. So the origin is your pole, right? Theta equals pi over 2 is your vertical line, symmetry about the vertical line. Okay. All right, 0, 0, 2.6, comma, pi over 6. 2.6, so circle 1, circle 2, circle 3. So 2.6 could be somewhere there, right? Not the mid mark, but little above the mid mark. It all looks like the mid mark to me, but it's okay. And 3, comma, pi over 4. 1, 2, 3. 2, comma, pi over 4. 2.6, comma, pi over 3. 0, pi over 2. Okay, see that 0 pi over 2 brings you back to the origin here. That so go for more coordinates if you'd like. For instance, you see that pi over 12 there, right? Plug in pi over 12. Pi over 12 will give us 2 times pi over 12, pi over 6, right? So pi over 6, sine pi over 6. So go back to this. Sine pi over 6 is a half, right? So 3 times half, which is 1.5. So come back here, pi over 12. So 1.5, 1.5 pi over 12. So likewise, 5 pi over 12, because of the symmetry, will also give you something like this. Now connect all of these. Look at that. That gives you the first petal, okay? And then use the idea of symmetry here and go ahead and get your other petals. So you can kind of plot these points, right? This mark, this mark. I can't even see what I'm doing. Okay, and then finish the other petals for the other remaining 2. You can pause the video and try it on your own. You could check with me once you're done there. And then went too fast on the other one. Okay, so you've got your 4 petals for your rows. So the orange one is the one we got from the graph. I'm sorry, what do I mean? Graph. I mean table. Table. And these petals graph using symmetry. And that is the end of 3.3. And I hope to see you in the next video. Thank you.